hello everyone. Thank you all for coming. And this is going to be like a little bit technical talk, but I will start from high level so everyone can understand me, and then Bernhard going to hit with all the engineering details. Like we are the Fluence working on a decentralized serverless platform, and you would wonder how is it related to all the RPC business, and I will tell you in a couple of minutes. So, but just initially the context for everyone. So there is a cloud computing business. It's like hundreds of billions of dollars. Like it's basically where all the backends of the whole internet live. Like all the most of blockchain nodes, unfortunately, live in the cloud, as we know. And there is on top of basically servers and infrastructure, there is the whole layer of cloud services that these big companies like Amazon and Google created over decades already. And one big segment of this cloud business is a serverless products. And it's sort of like the most comprehensive solutions that makes the experience of developers using it as simple as possible. So when you're using serverless, you're not thinking about limitations of particular servers of physical hardware. So you have this elastic scalability, you have great, like you can easily build stuff and you can iterate quickly. So at Fluence, we have this vision of bringing this serverless experience in a Web3, in the decentralized world, and basically building these serverless products. But details are more interesting here. So this is just a quick mapping on some products that Amazon has. Like basically, they have this functions as a service called Lambda, and we have functions in WebAssembly. They have step functions of workflows, and for this we have our own solution called Aqua, which I'm gonna talk about now. And they have a lot of like services that we also have analogy to them. But so quickly, again, like iteration on like Fluence is a decentralized network, so right, it's managed by DAO. It's built on top of the marketplace of different compute providers, so like anyone like who are running on their validator nodes or like running, you know, like a storage provider, so Filecoin, like people basically from the ecosystem can join as a compute providers and, you know, run servers like and be capacity providers for the network. And on top of it, there is a like developer tool set that allows easiness of use for developers. And using this tool set, you can create applications, and what kind of applications it could be. So you can, like, simplest thing is like, I have a piece of code, I run it in Amazon, so now I can run it on Fluence, sure. But more interesting thing is the all kinds of distributed applications or like multi-party applications, which are, if you think of this, which are our decentralized RPC solutions, like the example of it, right? There might be other examples like where you have basically several nodes that needs to talk to each other and somehow collaborate and somehow produce together the product. Like, for example, Oracle implementations, so like a bridge implementations, or you know, like you can imagine something crazy like decentralized messaging applications, right? And like decentralized RPC is one of the things that we think that would be really, really great to build using Fluence development stack. So yeah, so roughly the network looks like this. These are Fluence nodes run by different compute providers on the network. They all can execute any kind of code. And they are plugged to different external networks or Web 2, you know, infrastructure. They can call HTTP APIs, they can call like cloud service, traditional cloud service, but they also connected to like blockchains or like IPFS, like any kind of Web 3 infrastructure. So basically, then they organized to what we call subnets. It's basically groups of nodes that like group together based on certain logic, certain programmable logic. The basic logic is that basically the replication factor. Let's say you deploying the simplest piece of code to Fluence network. It means that you deploying simplest piece of code to several nodes, and your piece of code is replicated. So if one node goes down and doesn't respond, like the other node can basically execute your function. So it's sort of like the simplest use case of this deploying on subnets is a failover, so you have fault tolerance. But there could be much more different logic built in there. And this logic is basically can be expressed in a program. So you, to express this distributed workflow logic, we have this whole language and a distributed protocol that basically allows you to run distributed workflows without a centralized coordination place. Like if in Amazon, for example, you have these step functions that allow you to call this function, then that function, then that function, right? This step function, the language you're using to describe the workflow is they have JSON and they have a visual like editor where you can drag blocks. Here you have the whole programming language, which gives you much more power and much more flexibility of describing these network algorithms or workflows. And some examples of it, yeah, so like Aqua basically powers these subnets and powers the network. It's like lives everywhere between the nodes. So it's kind of like how requests being served by the network. Yeah, so basically you can express a lot of distributed algorithms as AquaScript. Like you can have consensus if you want. Like you can program consensus in Aqua and you can put it to your subnet if you need consensus. If you don't need consensus, maybe you need quorum. You can have quorum algorithm. Maybe you want to load balance between different nodes, or like have an algorithm that that optimizes latency between globally distributed nodes, so your RPC response is faster, right? So you can have the load balancing algorithm in Aqua. Like also replication, or like we have also examples on MPC when you have this threshold signature signing scheme that involves many parties and they collaborate on creating signature together. The cool thing about this thing is Aqua has verifiability built in. So whenever Aqua code is being executed, every node, like if you have like an algorithm, like let's say from this example, it's some kind of MapReduce, right? So I ask several nodes to give me price, getting from somewhere, let's say from external source, and then I'm calculating average at some other node and give it to the user. So this is like the simplest MapReduce, right? So here, every node, every next node in this workflow would be able to verify that the previous part of the workflow was executed correctly, that it was correct nodes who were involved, that the inputs and outputs are like correct, and the the initial user has the right to initiate this this workflow. So basically, like as long as workflow is being executed, it's being validated by the next nodes that involved in this workflow. And also part of our kind of security and incentive model, some of these workflows are probabilistically verified on-chain. And this creates you, like if you need audit log for your system, you can basically like show like to regulator or to your users that actually, hey, we did this RPC requests that you asked us to do, like we did this, we provide you this API response, which was combined from some other APIs, and this is the proof, like this audit log is a sort of proof that this was done as is supposed to be done. So we haven't really, like we didn't, change things in between under the hood, right? And it's all content addressable, it's all like compatible with IPFS, so it's very, very useful. And the last thing is, like, there's a payment model built in to the network. So, but basically, like, if you're using this, you can either use nodes that being run by some compute providers on the network. You can run your own nodes, for example. And then there is a way how you pay it. So currently, payments for the execution are in stablecoins, in USDC. We want to enable it for any ERC20. So it would basically means that if you are using Fluence to create your own like subnets to run your own workloads on it, then if you want, you can either agree with compute providers on Fluence network to accept your token or some other ERC20, or you can run your own nodes as a part of Fluence network, and basically this way make this payment happen in ERC20 instead of stablecoin. Yeah, and also like paying by request is coming. So now we're gonna switch to Bernhard, and he's gonna talk about like particular application of this to the RPC. We have like a showcase the implementation of decentralized RPC built with Aqua and Fluence.
All right, 2 pieces. Okay. Hi, I'm Bernhard. I already pre-apologize. My respiratory system and the Istanbul air quality do not entirely see eye to eye, so I have been coughing quite a bit lately. But hopefully it's not going to be too distracting. So now that you learned sort of everything you ever wanted to know about Fluence, let's put this to work and let's start out programming decentralized RPC. And we had an entire earlier session on this, but fundamentally, as a dApp developer or in the dApp space, it's almost prohibitively expensive to run high availability clusters of EVM nodes, particularly on the Ethereum side. It's just not practical, and as a result, we have RPC as a service, which is fast, which is cheap, which is great, it produces or provides great APIs, but we have this problem of single point of failure, data integrity, and privacy concerns. Many in this room are working exactly on solving these problems, so welcome and thank you. And we're going to give you our take on how the Fluence stack can be used by you, actually, to improve your decentralized RPC solutions. Nope. Okay. So, Evgeny pointed out we have different building blocks in Fluence. Marine, it's a WebAssembly runtime. This is where the WebAssembly containers come in. We have Aqua, which is your programming language. It also has a compiler and a few other nice things. And now we're getting into the FRPC thing. So we have to add a little bit to the solution in order to make it work and make it work in a decentralized manner. If you look over there, we have a dApp, and that dApp is actually self-contained. So when you implement with Aqua and Marine, you do not have to touch your dApp. You take that URL, your Web3 library you use basically pushes out, and that's what you consume in this FRPC. We call it a substrate because, as I said, it's not a product, it's an example on how to use Fluence. And the first thing you want to have a gateway, probably self-hosted, and that gateway is your HTTP to peer-to-peer bridge. Because as Evgeny pointed out, the Fluence network is a peer-to-peer network. And when you deploy your services, we'll get to that, which are actually Marine connectors at the bottom, you deploy them into a peer-to-peer environment. And you control where you deploy your services to, these connectors to. So you have a lot of optionality from literally from green data centers to geo selection, which becomes important when we get into some of the other things like privacy. Then from the gateway, you fire off this Aqua script. Like I said, it could be could have multiple algorithms, including a quorum, could have a failover, could have load balancing, and getting parameterized either through configuration or actually the JSON RPC request itself. So based on value of a particular method or by the method alone, you can start selecting which kind of distributed algorithms you want to put to work in order to optimize your process, your transactions, and your cost. Once you have this algorithm working, this Aqua working for you in this workflow, you basically initiate the endpoint call through your WebAssembly service, which is the Marine connector there. And that's actually the reverse of the gateway. This is an HTTP connector from the peer-to-peer network out to RPC endpoints. And in our suggested solution, I mean, you can use whatever RPC endpoints you want, but hosted RPC endpoints, I think, actually are really efficient. And if you have many different ones, you can really de-risk very, very significantly and very elegantly and very cheaply. So, in many respects, in particular around this RPC, the Marine connector is basically your HTTP request from the peer-to-peer network back out to the RPC endpoint. And maybe you can see it, I hope you can see it, it's here. And there's a little bit more to it, but fundamentally, even on the WebAssembly side, it's a very low-code solution that is very similar to your traditional request W in JavaScript or Rust or Python. if you want to write a particular algorithm, like a quorum algorithm, this basically is it. And the quorum algorithm is interesting because it actually helps you, or can help you, decentralize on two levels. It can help you decentralize on a single point of failure, because you will be calling multiple RPC endpoints at the same time, and on the data integrity side. So this is an extremely powerful approach on how to handle or how to decentralize RPC very, very easily. We also have a we're smaller here. It's basically a round robin algorithm implemented in Aqua. And if you look at the number of lines, I mean, those are very low code solutions that actually pack a punch, because that manage all the entire peer-to-peer topology within Fluence. So it's super powerful. Anyway, so that if you have a round robin, for example, we could do it randomized, but we also can cycling. So if we have 3 peers, A, B, C, we can keep cycling through them. That is actually, in some method calls, probably preferable over parallelizing, where data integrity may not be that much of an issue. And you can retain state outside of the DApp, which is actually super, super cool, because you can manage that state not just in, for example, cycling through your RPC endpoints. You can actually start tracking which of the RPC endpoints, if you do a quorum, for example, is performing as a constant outlier, and over time make longitudinal decisions where you start removing non-performing RPC endpoints and replace them with other ones. So this is sort of a decentralized high availability design based on that quorum algorithm. And again, we have our DApp, we have our method request going into the gateway, we execute that script. And now in Aqua, in this particular quorum algorithm, we decide to parallelize over n, k, whatever you want to call, 3 from a slide perspective, RPC endpoints. And if you're really, really paranoid about your transaction, you can actually go one step further and have every connector call every endpoint. I didn't put it on the slide because it gets very convoluted very, very quickly. And then, of course, you get your responses back, and then in Aqua, you resolve those responses against your quorum algorithm. So if you have unanimous response, obviously you have no problem. If you have a partial response overlaps, you can now start looking at what's my quorum threshold, 2 out of 3, for example. You can add initial or alternative requirements as well, like we have here, for example. We want a minimum result. If I make 3 calls, I want to have at least gotten 2 back. And those are all like very easily programmed into Aqua and then executed. And so now you say, hey, we wanted to eliminate single point of failure, so you bring an entire network to play here. How are you not going to be the single point of failure? And this is where the entire idea of the subnetworks plays a very big role, as Evgeny pointed out earlier. And we can resolve subnetworks which rely on you as a developer or as a decentralized RPC provider, where you say, okay, I'm managing 10 distinct RPC endpoints, hosted RPC endpoints, for example, and I'm deploying 30 of my marine connectors across many different peers and many different providers. That gives you a very, very large subnetwork, which you can very easily, like in a very low-code manner, manage, and that gives you the failover at the network level. So now you have failover at the network level, and you have failover at the application level. And this is how we tackle, or this is how we think, you should tackle or can tackle a single point of failures in RPC workflows with Fluence. On the privacy concern issue, there are also multiple ways where the peer-to-peer network at least helps you obfuscate your IP address. And there's things you can do because it was brought up earlier in terms of how to rewrite your packets, for example, when your headers, when you do your marine connector, if that's of concern. And if you have just your local gateway, your DApp IP goes into the peer, and then of course from the peer, the PRD goes to the RPC endpoint. So here we're really trying to work to preserve as much privacy, if you will, from the RPC endpoint, not the network itself. Within the network itself, we have very, very strong encryption, end-to-end encryption on the transport layer, and we also have on the Aqua layer encryption, which we don't have time to get into, but if you're interested in adopting Fluence, for example, to build out your decentralized RPC solution, come talk to us for sure. So what does this now actually look like? So you write this Aqua script, right? You have your gateway, and I'm here using our CLI, so it's not literally a gateway, but the CLI, to make a request. That request is quite verbose. It wouldn't be that verbose if you do it in the gateway or programmatically. But I also want it to be as explanatory as possible. And this gives you your method we want to call. This is your relay. So basically what, as I said, you connect to the peer-to-peer network. The way you connect to the peer-to-peer network is through a relay. Relay is a publicly available and accessible node. And then you start pumping through your various RPC URLs, which of course you can do through a configuration file. You wouldn't have to do this manually at all. And in a quorum type environment, and this is where we had 3 RPCs and we did, every connector did 3 calls. You now get from every connector, you get your block heights back, for example. And in this particular example, yes, they all line up, so this was a good day. Sometimes this is also like a really great feature and super important. If you get a quorum result back, you don't necessarily, depending on the method you're using and or the parameters with the method, you can programmatically decide within Aqua that you actually don't want to accept the quorum result, but you want to repoll. Again, this logic is outside of the dApp. Your dApp is not affected by it at all, which gives you a really, really high degree of flexibility to build generalized solutions. So that was sort of the quick intro into how to program decentralized RPC solutions with Fluence. We went through all the major points where we want privacy. The additional aspect, and Evgeny mentioned it, there's a verifiability aspect to it. And if that's something of concern when you build solutions, you basically get this for free. And that's actually, it could be very, very powerful depending on who your customers are when you do this. Other than that, stay in touch, reach out. We're here, obviously, for the rest of the day and for the rest of the week. Twitter, well, we get them all. Well, Discord. And
thank you, Bernhard and Evgeny.